Hey everyone, welcome back. This will be part B of lecture 5. And so I just want to recap the problem we just looked at. So in this problem, we were evaluating 1 to 5 of the integral from 1 to 5 of x divided by the square root of 2x minus 1. Okay, so this is the integral we were looking at. So there's a couple of things substitution wise that we had to do here. So we start with by setting the u equal to 2x minus 1 the square root, which throws a number of people because you might want to say it's 2x minus 1, but this is also like a rational function, right? So you've got this piece down here in the denominator. The whole denominator should be set to u, and we can use this to find a substitution for x, right, by just squaring both sides and then solving here. X equals u squared plus 1 over 2, right? If we differentiate u, we have to use the chain rule, right? So du, the derivative of this, would be 1/2 2x minus 1 to the negative 1/2 times 2, which we get, ultimately we get 1 over the square root of 2x minus 1, which is 1 over u. Okay. Well, I need to write that there, 1 over u dx, right? Okay, and so then that ultimately implies that dx equals u times du. Okay, and so this piece here, together with this piece here, and this piece here, those three pieces can be used to substitute into this expression, 1 to 5. So the x is u squared plus 1 over 2, and the denominator here is just u, and then the dx is u times du. Okay, and all of this simplified down greatly into 1/2 times the integral x equals 1 to x equals 5 of u squared plus 1 du. Okay, and then we did calculate the rest of this in the previous lecture, but I want to make sure to point out, to go back and recap this, because these were, I mean, this piece here in particular and this piece here in particular can be a little confusing, right? The way that I would recommend you kind of think about these u substitutions is, look, I mean, any valid algebraic technique that is necessary here can pretty much be used. So you can basically, if we, look, if I'm stuck with this x up here, I need an expression for x in terms of u. I can just use this, do the algebra needed to get x in terms of u, and just plug it in, right? And similarly over here, if I need an expression for dx, I can just do whatever algebra is necessary to get dx written in terms of u and or du, or some constants. Okay, so there's, some of these integrals will not obviously fit the pattern of, f of g of x, g prime of x dx. They won't always fit that pattern, obviously, but very often you can force them, force a fit using different algebraic techniques. Okay, so even with change of variable methods like this, integration can at times be very difficult still. So there's a lot of other little tricks. I mean, obviously we're going to learn a lot more techniques, but one such technique would be the recognition of the integrand as either an odd or an even function. So just to remind people, even functions, they satisfy the following: f of x equals f of negative x. But what this basically means is that they're symmetric across the y-axis. A great example would be like any quadratic equation. well, not any quadratic equation, but a quadratic equation that maybe looks like this. Okay, so maybe this is some value negative a. This is the value positive a. You can see that the function is a mirror image of itself across the y-axis. Okay, so this is an example of an even function. An odd function is one where negative f of x equals f of negative x. Right, so if you plug in a negative into the argument, then it makes the whole function negative. These are functions that are symmetric about the origin. Okay, so an example would be something like this. Okay, maybe you've got your negative a here and your a here. Okay, so these are kind of flipped about the origin. Okay, so something emerges when we are evaluating definite integrals of an even or an odd function, and it can frequently be used to your advantage. So let's talk this one out quickly. Let f be integrable on AB. Oh, sorry, actually not AB. We're going to make it a symmetry here. Negative a to positive a, so kind of like what we were drawing here. Then, 1, if f is even, then the integral from negative a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. Now, even functions are functions that are kind of like this, right? So they're symmetric across the y-axis, right? So obviously the area from here all the way over to here is just going to be twice the area from 0 up to a, right? That's just because of the symmetry of the function. Okay, so that's the first part of the theorem. What happens for odd functions? If f is odd, what do you think? Negative a to a of f of x dx. Well, so think about what's going to happen here. You'll have this part here, that's 0 to a, and this part here, that's negative a up to 0. They're going to be the same in terms of the absolute value of their area, but this is positive, and this is negative, right? So they offset each other perfectly, and so that that integral will be 0 every time. Okay. All right. So let's go ahead and prove this. Let's just prove the even one. Okay, we'll prove the even side of the expression. All right, so proof. So let f be even. Okay. Then f of x equals f of negative x. Okay. All right. Letting u equal negative x, we have du equals negative dx. So we're doing a u substitution here. Okay. And so we'll start with the negative a up to 0 piece. F of x dx. Now, what we're going to do here is we're going to rewrite this as the integral of f of negative u times negative du, right? And that comes from right here. If du is equal to negative dx, then dx is equal to negative du. We need to adjust the bounds here. So instead of negative a, the lower x is equal to negative a, then u is equal to negative a, which is just a. Okay, so I get a here. On the upper, if x is equal to 0, of course, the bound will stay the same, right? Negative u is equal to negative 0, which is 0. Okay, so that's that. And so then I can kind of deal with these negatives. So f of negative u is just f of u, and then this other negative comes out. So this would actually be equal to negative a up to 0 of f of u du. Okay, and then I'm going to rewrite this as a positive integral from 0 up to a of f of u du. Now what did I do here? I just used this fact from a couple sections back, that if I have the integral of the negative integral of f from a to b, that's equal to the integral from b to a of f, right? So the signs, the limits can flip, and it changes the sign in front of the integral. Okay, so I've got this piece here. Okay. All right. So then what I want to do is consider this. So negative a up to a of f of x dx is equal to negative a to 0 of f of x dx plus 0 up to a of f of x dx, right? So we've got that piece there. And this one down here, right, we just saw that this piece here is right there. So, right, so negative a up to 0 is the same as this. And so basically I can substitute that in. 0 up to a of f of x dx plus 0 up to a of f of x dx, and obviously that's equal to twice 0 up to a of f of x dx. Okay, so kind of a straightforward, I mean, we use some moves, right? You have to be careful here to get the bounds changed correctly, and then of course this one we've used a number of times. It's extremely useful, but you have to be a little bit careful there. But then it just falls right out, right? It's basically just take this piece here, rewrite it as that, and then write it as 2 times. Okay, so that one is very very straightforward. Very straightforward. Okay, I'll leave part 2 to you guys if you want to spend some time working that out. It's a good idea. Let's do an example here using this even-odd theorem. So definite integral from negative pi over 2 up to pi over 2 of this mess, sine cubed x cos x plus sine x cos x. Okay, so just recall that sine of x is an odd function, and so sine of x is odd and cos x is even. Okay, so then if sine of x is odd and cos of x is even, what is this? It's it's basically just a bunch of sines and x's kind of multiplied and added together. Can we determine whether it's even or odd? We sure can. We can evaluate f of negative x, and we'll say that's sine of negative x cubed times cosine of negative x plus sine of negative x times cosine of negative x. Okay, just plugging in negative x. Now, sine of x is odd, so that means when you see a sign of negative x, that's equal to negative sine of x, like so. Cosine of x is even, so that means cosine of negative x is just cosine of x, like so. So this would be negative sine of x, and this would be cosine of x. And so what happens here? So this would be a negative times a negative times a negative. So that whole thing is negative. And so you get negative sine cubed x cos x minus sine x cos x. Okay, and so you could factor the negative out. Like so, and you can see then that that is negative f of x, isn't it? So f of x is this piece inside the parentheses, the negative sign is out front, and so that means that f is odd, right? Well, that makes our lives very simple, right? Specifically, that makes our lives simple because if f is odd, and the definite integral that you're interested in is symmetric about the origin, which it is in this case, then pi over 2 to negative pi over 2, that integral of an odd function is 0, right? By the previous theorem, right? By the previous theorem. Okay, so basically that means this integral up here is equal to 0 because f is odd and the region is symmetric about x equals 0. Okay. All right. So this integral, I wouldn't want to have to do it. I wouldn't want to have to calculate it. But we don't have to in this case, right? We can use this odd, even odd theorem to determine that it's 0 without doing any other work. Okay, very good. That's it, I think, for lecture 5 of this class. Next time we'll get into what's called numeric integration, and so this will be how we deal with integrals if we can't actually integrate. If the function doesn't if there's no elementary, antiderivative available, what do? Well, we can still calculate definite integrals. We just have to use a little bit of tricky computational work. And so it's actually a very super interesting section. So be sure to check it out. We'll see you then.